Okay, class, let's start. So, if you remember, I'm just going to share the screen with you. If you remember, I started with this result that every zero of an analytic function has finite multiplicity, right? Class, can you see the screen?
Yes, sir.
Okay. So last time I was doing this corollary that every analytic function defined on an open connected set, then it's every zero has a finite multiplicity. So if you remember, I ended up with this step number one, and then you must have seen that before posting my last week notes, I added up this comment also. So I think now there should be no confusion. Actually, it depends upon that how you uh, take it up. It means uh, if you if you focus at this n, then this is the smallest, and if you focus at n so that derivatives up to n minus 1th order are 0, then you can say that such n is largest. Largest means that in the sense that at the most derivatives of the order up to n minus 1 are 0, and after that the derivatives uh, the uh, the nth order derivative is not 0. So I mean it's up to you, and I think now there should be no confusion regarding the fact that ultimately at nth stage there is some nth stage at which the derivative of the function at a is non-zero. So I'm continuing after this now. Okay, so continuing with the proof. Now define the function g from g into c as, so we are defining function g like this. When z is not equal to a, we are defining the function gz as fz upon z minus a to the power n. And here, remember this n is exactly this n. Okay. And when uh, z is equal to a, we are defining the function like this. So clearly, uh, the value of g at a is non-zero, as you can see here, class, the way we have defined it. This is just by definition. And fz is z minus a to the power n gz. if you notice. Is this okay, class?
Yes, sir.
Of course, when
For
I am
all z not equal to n, sir.
yes, yes, of course, here z is not equal to a. That is understood. This is just the definition. Now, uh, now since GA is not equal to 0, this automatically implies, class take a note, that uh, A is a 0 of f having multiplicity how much? N. Yeah, because now A can't be a 0 of Z more than n times, because the value of G at A is not equal to 0. So it means it can't be the 0 of F once more. So A is a 0 of F having finite multiplicity. Multiplicity n means this n is finite automatically. We know this. Okay. Now, the only thing what I am left to show now is that I am to show, as per the statement of the theorem, that we are to show that this G is analytic. We are to show only this now, that this G is analytic. So uh, we are to show that G is analytic. And once we have shown that G is analytic on G, the proof will be complete. Now, clearly, G is analytic on G minus A. Class, if you take uh, uh, Z not equal to A, then you can clearly see that G will come out to be analytic. Reason being the way it is defined. If you notice, if Z is not equal to A, then F is analytic on G, and Z minus A to the power N. This is a polynomial expression. This is also analytic. So using the algebra of analytic function, this expression is analytic. Is this okay, class? So it means GZ is analytic whenever Z is not equal to A, right?
Yes, sir.
Right. So clearly means in view of the algebra of analytic functions. क्लास किसी का माइक ऑन है, प्लीज म्यूट करके रखें. Okay. So finally, that is, we are just left to show the analyticity of f at A. So once we have shown that f is analytic, sorry, क्लास किसी का माइक ऑन है, प्लीज म्यूट योर सेल्फ, प्लीज म्यूट योर सेल्फ. मिस्टर नवीन, मिस्टर नवीन, मुस्कान, गौरव, प्लीज म्यूट योर सेल्फ. Class, do you want to continue me? Naveen, please mute yourself. Muskan, Gaurav.
So I am muted only.
सर हमारा भी
Okay,
म्यूट हो रहा है.
Muskan, you. Mr. Naveen, Naveen Sherawat, Mr. Naveen. Please mute yourself, Mr. Naveen. Okay. So class, finally we are just left to show that G is analytic at A. Okay, and for this class we are going to adopt this approach. We will just show, we will show that G has a power representation in a neighborhood of A. So class, if we show that G has a power representation in a neighborhood of A, then you know that G must be analytic at A. Is this okay, class? So we will be using this approach. Is this okay?
Yes, sir.
Yeah, so if you want to note down the reference, this is I am saying so in view of corollary 2.9 at page 37 of your book. So in view of this corollary, it will be sufficient enough to show that G has a power series uh, representation in a neighborhood of A. So finally, I am going to show you this. So once we have shown this, it will be established that G is analytic A. The analyticity of a small g at G minus A is just obvious using the algebra of analytic functions, and the proof will be complete. Okay. So to that first class, I show that G is continuous at A. So for this class, I am starting like this is equal to, sorry, this is equal to limit z tending to A fz upon z minus t to the power n. Is this okay, class? This is the definition of Gz. Of course, you know that when we are taking limit at A, then we consider deleted neighborhood. So it means in this expression, we know that denominator is non-zero. Is this okay, class? And now, class, you can see that this is certainly 0 by 0 form. Yes or no? If you take put z is equal to a in the numerator and denominator, it will be 0 by 0 form, right, class?
Yes, sir.
So what you can do is the L'Hopital rule can be applied for complex valued functions also. So let's apply L'Hopital rule. So class, if we apply L'Hopital rule, then what? So you know that class how to apply L'Hopital rule. According to L'Hopital rule, this limit will further be equal to this limit will this limit will just not class. Class, just a minute. Yeah, this limit will further be equal to class. You will take the derivative of numerator separately, and you will take the derivative of denominator separately. Yes or no, class? This is how you perform
Yes,
L'Hopital,
sir.
right?
Yes, sir.
Yes, sir.
Yes,
Uh,
sir.
Class, you can see again. If you take z is equal to a, then numerator is again 0 and denominator is again 0. Yes or no?
Yes, sir.
Yes, sir.
Because if you recall class, then uh, derivatives up to n minus 1th order of f are 0. Right, class?
Yes, sir.
Okay.
Yes,
So
sir.
class, you perform L'Hopital rule once again. So this will be limit z tending to a, double derivative of the numerator divided by, it will be n into n minus 1 into z minus a to the power n minus. And class, again you can see it is 0 by 0 form, right?
Yes, sir.
Yes,
Yes,
sir.
sir.
You go on doing this. So at the nth step, class, you will have something like this. Nth derivative of a, and in the denominator you will have n minus 1, n minus 2, and going up to 2.1. Are you getting me?
सर एफ एन जेड होगा.
Yes, class. Sorry. Sorry. Yes, sorry. Thank you. Sorry. Thank you. Yes. So class, you can see, and if you allow me, this is nothing but n factorial. And
Yes,
now
sir.
class, we are out of 0 by 0 form. So this will be finally equal to, you know that, simply, because you know that f is analytic. So f is infinitely differentiable. It means derivative of f of every order is continuous. So when you take limit z tending to a, so you can take it inside. Is this okay, class?
Yes, sir.
And this is nothing but what, class? The value of g at a. This is how we have defined g, right, class?
Yes,
So
sir.
I have shown you that the limiting value of g at a is coming out to be equal to the exact value of the function g at a. This implies what, class? That g is continuous at a. Is this okay,
Yeah,
class?
it equals to a. Yes, sir.
Yeah. So it is continuous at a. Okay, good enough. And hence on g. Why? Because on rest of the part of g, this is already analytic. On g minus a, this is already analytic. So at g minus a, it is already continuous, right, class?
Yes, sir.
Okay, fine.
Yes, sir.
Yes, sir.
So class, if g is so, and therefore class, so okay, now g is continuous, number one, this we have, and the value of g at a is not 0, the way we have defined g, class, and therefore there exists some r greater than 0 such that, in fact, class, I am saying that there exists a ball in g centered at a, such that inside this ball g will remain to be non-zero. If you remember, class, once, I think in last class or in last to last class also I used this result, that if g is continuous, then there will be and it is non-zero at some point a, then there will be at least one neighborhood around a, that in that neighborhood function will remain non-zero. Do you remember, class? I used this result,
Yes, sir.
right? So and I give you a reference also, that this result is from Brown and Churchill. I mentioned the page number also, if you remember. Okay. Now class, uh, since f is analytic on BAR, certainly, class, because f is analytic on G, and hence it must be analytic on BAR, which is nothing but just a subset of G. Is this okay, class? Right, class?
Yes, sir.
Yes,
Right,
sir.
right. And you know that if f is analytic on BAR, then we have already done this result, that if f is analytic on such a ball, then we can write power series representation for f on this ball. Right, class?
Yes, sir.
We've already done this result. So since f is analytic on this,
Yes, sir.
we have uh, fz is equal to, we have this power series representation. This is centered at a and is going from 0 to infinity for all z in the ball. We can write its power series representation, class, where, class, it is easy to note that ak, you if you remember, the AKs were defined like this. Coefficients were defined like this. Yes or no, class?
Yes, sir.
So clearly, class, ak is equal to 0 for k is equal to 1, 2, 3, and up to n minus 1, and an is non-zero. See, class, here, this, is this okay, class?
Yes, sir.
Right? So the coefficients starting from 0, okay, sorry, starting from 0, 1, 2, and up to n minus 1, these coefficients are 0, and the nth coefficient is non-zero. Okay, so therefore that is, if the coefficients up to an minus 1 are 0, so class, I can simply write fz like this: ak z minus a to the, oh sorry, we should have n here, a to the power k, and now k will start from n. Is this okay, class? Because the coefficients up to n minus 1 are 0. Is this okay? Is this okay, class?
Yes, sir.
Now, this is equal to,
Yes, sir.
what I do, I further make use of this n. It is exactly that n, class, if you remember. It is exactly this identified n, which we identified in the beginning. It is this n. So now this is further equal to, class, summation k is going from n to infinity ak z minus a to the power k minus n. I think you must have noticed, class, this is a manipulation step. What I have done, I have taken this power of z minus a outside. So inside I have this power of z minus a. Is this okay, class?
Yes, sir.
The simple algebra. Or, class, I can say fz upon z minus a to the power n is equal to, k is going from n to infinity ak z minus a to the power k minus n for all z which are not equal to a and in b, except the center, because certainly otherwise fz upon z minus a to the power n will have no meaning. So except the center, I can write this expression, class, for all other z's. And if you remember, by definition, when z is not equal to a, this is gz by definition, right, class?
Yes, sir.
Yes.
Right? So that is gz is equal to summation k is going from n to infinity ak z minus a to the power k minus n for all z not equal to a, and the z's are in this. Where, class, you can easily notice, as I told you, you just uh, take the, where ak is equal to nothing but this. You can easily notice that if you recall what process I adopted for this. You write the full expression for gz is equal to, you just open the series and you take its derivative once, twice, or like this. K is equal to n, is equal to n plus 1, and so forth. Is this okay, class? Is this okay?
Sir,
Yes?
sorry, for all A not equals to Z, Z belongs to B, A capital R आएगा ना?
Uh, oh, sorry. Sorry. Thank you. Yes, it was capital R. Small r पता नहीं कहाँ से आ गया. Okay, is this okay now? ठीक है? Is this okay, class? अरे
Yes, sir.
गलती गलती यहाँ नहीं, गलती यहाँ है. अरे भाई यहाँ ये स्मॉल आर ही लेके चल रहे हैं.
सर
गल...
ऊपर स्मॉल आर के
हाँ हाँ, उस ऊपर स्मॉल आर.
हाँ सर
वो कोई बात नहीं, ठीक है, वो आप समझ गए. स्मॉल आर है, सॉरी. थैंक यू. So we have gz is equal to this whenever z is not equal to a, and class we can write this, or we can write gz is equal to summation m is going from 0 to infinity bm z minus a to the power m, where bm is equal to am plus n. Class, please take a note. The only, if you notice here, the dummy is k. This n is fixed, right, class? Right, class? The dummy is k. Actually, the summation is over the index k. So I am taking an advantage of that, and that's why I am ignoring the presence of n because it is constant. So I am taking this notation bm is equal to am plus 1, and this is equal to the mth derivative of a divided by m factorial, where m's are changing from 0 to infinity. And now, class, if you notice, this is the above one, this is the, now I have this way, I have included a automatically, class, if you notice. Can you see that if you open this series, you will have g that is equal to b naught into b1 z minus a plus like that. And if you take z is equal to a, then b naught will be za. And from here you can see that b naught is za. Is this okay, class? So I have written this expression very intelligently. Is this okay? Basically the point is that, class, that you are seeing that this is power series, but here this z is z equal to a is not allowed. So what I have done, I have simply added the value of gz corresponding to a. So I have simply added ga to this. But then the point was that our coefficients should be of this type. Then to write down the final representation so that it appears exactly in the form of power series where the coefficients should be of this type always, I have done reindexing. Is this okay, class? So this is the power series of G on BAR. And now we are done. This is exactly where from we started. So once we have shown that G has power series on this open ball, this was our approach. So once we have shown that G has a power series representation in a neighborhood of A, hence G is analytic at A. Thus G is analytic at A, and hence on G, because the analyticity of small g on g minus a was already established trivially. Is this okay, class?
सर
Yes.
ये इंडेक्सिंग चेंज करना है सब कुछ समझ नहीं आया
Okay. No. Actually, okay, what you do simply, you just tell me one thing. The uh, only thing is that, for example, you take m is equal to 0. No problem. Just a minute. Okay. You take m is equal to 0. Is this okay? Who asked me this? Arju.
यस सर
Okay. You take m is equal to 0,
यस
right?
सर
No problem. What you do, I mean, this is up to you how you do it. Okay, I'm explaining it now. Don't worry. So you write this. So according to this, what will be gz class? Class gz will be equal to you start from k is equal to n. So it will be for class this will be equal to uh, an, just an plus, if you remember, okay, class, is this okay? Take k is equal to n, so it will be an, because z minus a to the power n minus n will be 0, that is 1. Is this okay, class?
यस
The
सर
next term will be take k is equal to n plus 1, and now you will have first power of z minus a. Is this okay? If you take k is equal to n plus 1 here, is this okay?
यस सर
And now the next term will be z minus a square plus a n plus 3 z minus a cube. Is this okay, class? Is this
Yes,
okay?
sir.
Now this is the power series representation. Take a note. Here z is not equal to a, number 1. Number 2, we know that when we have power series representation, the coefficients should appear of the type. Suppose it is function g, then its coefficients, let us say ak's are the coefficients, they must appear to be of the type this. Yes or no, class?
यस सर
Only then and then it is the required power series representation. So to this, what I have done, now you have a look at this. So basically what I have done, I have added to this. Now see, so what I have done, if you notice, class, the value of, if you want to use this power series for z is equal to a, because if you remember, whenever you are writing power series on BAR, then certainly you must be able to write it for all z in this. I mean, the center must also be included, if you remember, right? Because whenever you write power series representation like this is how you write power series representation, na, class? And what is its full form? If you expand it, it looks like this, class. Yes or no?
यस सर
And then what is the value of f at a?
ए नॉट
A naught, yes. So if you remember, we don't exclude the center, na? So, but if you notice here that if I take z is equal to a, then it means the value of an is g at a. Yes or no?
यस सर
Right. So it means the point is that the value of the constant coefficient, if you notice, at present it is behaving like as the first the term of the series. This is behaving like as the second term of the series. This is behaving like as the second term of the series. Yes, or third term of the series. Yes or no? You just
यस
try to think it that way. So what I have done is, then to give it a proper form, now you focus on this. So if you open gz is equal to, now you take class m is equal to 0. So class, if you take m is equal to 0, it will be am. Yes or no? Gz is equal to b0 is equal to am. Yes or no, class? Sorry, a n. Yes or no, class? An. And class, what is an? This is ga. So by reindexing, what I have done, now my B0 is coming out to be ZA, because class, whenever we write power series representation, our habit is to uh, see power series in this form, starting the coefficients from B0, B1, B2, and they should satisfy this kind of formulation. So this kind of reindexing is helping me to fulfill my these basic requirements, so that now I am fully convinced. Though here also, from here itself I could declare, that this is the required um, uh, power series representation for the function g on the whole on the this ball BAR. But certainly someone of you could ask me, sir, you are not including z is equal to a here. But by taking this kind of indexing, I have included this kind of uh, I have included z is equal to a also, because here also z is equal to a is automatically included, because this is defined at z is equal to a. At z is equal to a, the nth coefficient is coming out to be GA. But if you remember, your habit is to see that the A0 should come out to be equal to the value of the function at that point. So then certainly someone of you would have asked me, sir, this is the nth coordinate which is coming out to be equal to FA, but we should have the very first coefficient equal to FA. So just to address all those questions, we do this kind of reindexing, so that we are fully convinced that it is exactly of the required form. Is this okay, class?
Yes, sir.
Yeah, so that's the purpose. Otherwise, for me, I mean, the level at which we are doing the things, here itself it is enough just to declare that we have got the required power series representation of the function g on this ball. But just to make you the things more clear, I have taken this next step with the help of reindexing. Is this okay now?
Yes, sir.
Right? So this was just this was just a rough explanation. So don't get confused with it. I will keep it here. Don't worry. This was just a rough explanation. I'm not going to erase it. So class, this was a corollary in which we did that an analytic function. So any zero of an analytic function always has finite multiplicity. Now, class, we are going to take another important result. Very important information this result gives us. I will explain you. Just let me write down the statement first. So, class, let f from g into c, this be analytic function. And one important information about f given is that it is not constant. This is not constant. Let a be some point in g such that the value of f at a is 0. So it is given to you, class, that there is some point in the set g at which the function vanishes. So the class result says, then there exists some r greater than 0 such that f z is not equal to 0 for all z in this ball. Of course, this is understood that, class, this ball is contained in G. You are not going to go outside G. So what does it mean simply, class? It simply means this, class, that here is this point A. At this point A, the value of the function is 0, right, class? So this result says that there will be at least one neighborhood around R, at least one. That at so that at all other points in this neighborhood, the value of the function will be non-zero. It means what, class? That it means, class, that is, in this neighborhood there will be neighborhood in which, in this neighborhood, f can't have what, class?
Zeros.
Yes, any other zero.
Yeah, other than A.
Other than A, yes. Other than Z. It means what, class? It means if A is a zero of F, then any other zero of F will be at some distance from the this A. Because the moment we say that that is at some distance, it means what, class? So exactly I'm saying the following thing. So if A is zero, then some other zero will be at some distance. And if it is at some distance, then class, it means if A is not equal to B, then class, that we are in metric space, C comma DU. And if you remember, class, for these two metric space, if 2 points are distinct, then we can always separate them by two open balls.
Yes,
That
sir.
one of them will be centered at A and another one will be centered at B, and both these balls will be disjoint. Do you remember that result?
Yes.
Two distinct points in a metric space can always be separate. In topology, you will read this concept in the name of Hausdorff. Every metric space is Hausdorff.
Hausdorff space.
Yeah, every metric space is a Hausdorff space. Point separation property, is this okay? So if it means that any other root of B or zero of F will be at some distance from A. And if at some distance, then certainly you can have this. It means inside this ball, there will be no zero other than A, right? This is exactly what this result is saying. It means any two zeros of such a function are at some distance. Yes or no, class?
Yes,
Yes,
sir.
sir.
And at some distance, being at some distance, we call in terms of the metric space theory, isolated. Isolated means what? Isolated means at some distance, which is a little away from the other points, right, class? So basically this result says that is the zeros of an analytic function are isolated. If you have an analytic function, then there will always be some gap between its zeros. Is this okay, class? It's a very important result. Is this okay, class? Is this okay, class?
Yes, sir.
It's a very important result. Okay. So it means, class, what? See, class, consequence of it, very nice consequence. Suppose, class, you have a polynomial here. You have a polynomial here. Now suppose z is equal to a is a point at which the polynomial z is having value 0, for example. Then it means, class, what? It means, class, that there exists at least one neighborhood around A, deleted neighborhood, of course, where the value of qz will not be 0. Yes or no, class?
Yes, sir.
Right? And it means, class, what? It means that I can talk of pz upon qz in that neighborhood. Yes or no, class?
Yes, sir.
So except at A, I can talk of this expression in that neighborhood, and hence I can talk of this limit. Because, class, take a note, whenever you want to take limit of a complex valued function, that A must be cluster point of that. So because now in this ball, you are having issue only at the center, and all other points in the neighborhood are available. So passing through these points from any direction, you can take an attempt to approach A. So you can talk of limit. Is this okay, class?
Yes, sir.
So this is a very important consequence of this result. That allows us to talk of this limit kind of concept for the functions of the form pz upon qz, even if the function, the denominator is 0 at some particular point. Because this result, class, this result guarantees that if, and you know that qz, the polynomials are analytic, class, they are entire functions. So it gives us guarantee that if q is 0 at a, then certainly you are going to get some neighborhood where q will not be 0, and in that neighborhood you can take an attempt through the points of that neighborhood. You can take an attempt to approach the point a, and hence we can talk of this idea of limit at a. Is this okay, class?
Yes, sir. Yes.
Oh, this is really something very important. Okay, class, let's look into the proof. So proof is not that difficult, but still interesting. See, class. Now since f is non-constant, we have that f can't be identically 0. Now class, some one of you may ask, sir, why you have written if function is non-constant, then perhaps there could be this possibility also, that the function f is not identically equal to some constant. Yes or no, class? Where alpha is some non-zero constant. But I have taken particularly 0. How? Right, class? If you say function is non-constant, then straightforward, how you can say that the function is not identically equal to 0? Non-constant means simply it is not identically equal to some constant. But I have taken here 0. Right, class? So
Yes.
I am going to explain you that why 0? Why not any alpha non-zero? Because non-constant means simply this. Yes or no, class?
Yes.
Yes.
But I have taken 0. So that makes sense. See how. So I'm going to explain you this, especially why we can take 0. So see, class, if f is a constant function, let's take a note of it. Then class, you can have two situations. Number one, class, fz is equal to some alpha, where alpha is not 0, and this is for all z. Yes or no, class? One can be this thing. Is this okay, class?
Yes, sir.
And one can be this thing. There will be two cases only. Either function is taking 0 value always, or it is taking value equal to some non-zero constant always. Is this okay?
Yes, sir.
But but if you take this case, class, in this case, f will have how many zeros?
No 0.
Very good. No 0. Because 0 means at some point z the value must be 0. But you are taking some constant which is non-zero, and that will be a violation to our given fact. We are strongly given that there exists some a at which the function is taking value 0. Is this okay, class? So this possibility is ruled out, right? So only the second possibility is left. Is this okay, class?
Yes, sir.
Right.
Yes, sir.
Now see, so if this is 0, it means this is what you say as, that is, f is identically equal to 0. It means this, na, class?
Yes, sir.
And class, if identically equal to 0, then uh, then nothing to discuss. Sorry. can say, which is a contradiction. Why, class? Because your function is given to be
Non-constant.
non-constant, right? Right? So, I mean, this possibility is also ruled out. Is this okay, class?
Yes, sir.
So this possibility is ruled out because of the fact that we are given that at some point it must be zero. So if you rule out this possibility, then it means you are left with the possibility that fz can't be identically equal to zero, because this includes the possibility that there will be some point or can be some point at which the function is zero. Is this okay, class?
Yes, sir.
Right? So that's why I have written here this zero. So it's fully justified. Well thought of idea. Okay. So now, so class, if fz is non-zero, then class, by theorem 3.8 at page 78, what I can say about this set? Then the set A is equal to collection of all those z's in G such that fz is equal to 0. This has no limit point in G. Class, if you remember, in that theorem we did three equivalent conditions. The first one was if f is identically equal to 0. Then the second was that this kind of set will have at least one limit point. Do you remember?
Yes, sir.
Yes, sir.
Should I show you that result? Just a minute, class. Sorry, here it was. Where that result was. Yeah, it was this result, class. So this result says that these conditions are equivalent. It means class A and C are equivalent, right? Right, class?
Yes, sir.
Yes, sir.
If f is identically 0, then this set, this is nothing but set A. This must have a limit point, but in our case f is not identically 0, so it means this can't have a limit point in G. Is this okay? So I am using this theorem. Is this okay, class?
Yes, sir.
So class, if A has no limit point in G, it means what, class? It means, class, that is, we take, that is, if we take any A in G, then there exists some r greater than 0 such that the intersection of this ball with A will be empty. Is this okay, class?
Yes, sir.
Or it will be empty or just A? How does that matter? Is this okay? I mean, it should be empty. It should be different. Otherwise, to become limit point, it should be different from the center, and it should be different from being an empty set. So if it has no limit point, then this intersection must be empty. Is this okay, class?
Yes, sir.
It means what, class? This implies that for all z in BAR, what you can say about the values of f at these z's? None of these z's is in A, because the intersection is empty. Yes or no, class?
Non-zero value.
Yes. So if they are not in A, so what is A? A is the collection of all those z's where f vanishes. But if these z's are not in A, because this intersection is empty, So the value of f at these z's must be not equal to 0. Is this okay, class? Is this okay, class?
Yes, sir.
Is this okay, class? Of course, except, class, no need to bother, except at a, where we are already given that the value of f is 0. So other than a, is this okay? Because if you remember, class, to become limit point, this intersection must be not equal to this and must be different from the center. This is the complete definition. So other than a, it means at all other points the value of f must be non-zero. And it means what, class? That is BAR is the required neighborhood. We wanted just to find out a neighborhood, na, of a.
Yes, sir.
So that the function is having value 0 at a, and at no other points of the neighborhood the function has value 0. And that's done. That's it. We wanted to find a neighborhood, and we have been able to find a neighborhood where the function does not vanish. Right, class? So the key role is being played. You can see that how nice the statement is. You are given this fact, how you made use of this. You are given that the function is non-constant, how you have made use of this. And with the help of this, jotting down to this, how you have made use of this theorem. Is this okay? So it means, class, if you have an analytic function and you are given some root of the analytic function, then certainly around that root or around that 0, you can always find out a neighborhood, maybe a very small neighborhood, such that in that neighborhood, function is not going to get vanished at any other point of that neighborhood, except the center A itself. Is this okay, class? Is this okay, class?
Yes, sir.
Yes, sir.
Now, class, we are almost towards the end of today's class, and in this section now we are left with the last item, what is called as the maximum modulus theorem. Very important, maximum modulus theorem. Actually, we have three different versions of this theorem in our course. So, class, maximum modulus theorem primarily tells us that if you have a a an analytic function, and suppose there exists some point in the domain such that the maximum of the analytic function is obtained at that point. It means, simply I am saying that suppose you have analytic function and its maximum is attainable, then this class, this result says that function has to be constant. This is something which is quite contrary to the real valued function. Class, in real valued functions, you know this trivially, that if you have a differentiable function and it attains its bound, it means there is some point in the domain at which the function takes maximum value. Then there is, I mean, we can't ever say that function is going to be constant. You take any example, any differentiable function defined on a closed and bounded set for real valued functions, you will see that it will attain its bounds, because differentiable means continuous and every continuous function attains its bound. But certainly that's not going to be constant, general. But in the case of complex valued function, if you have an analytic function, it attains its bound on the domain of definition, then it has to be constant. Something, I mean, a very strange phenomena. So this is a very important theorem, and it has a lot of severe consequences in the theory of complex valued functions. This theorem has a nice proof. We have three variants of this theorem in our course. So next time, that is on Thursday, I shall be starting with this and its variants. So let's stop now, class.
Excuse me, sir.
Yes.
सर एक बार वो वाला चीज दोबारा बता दीजिए कि हमने उसको 0 क्यों लिया है अगर वो नॉन कांस्टेंट गिवन है तो.
Okay. No issue. Just a minute. यहाँ से हम दोबारा, you are asking about this, right? You are talking about this one, this and this, right? Is this okay? You are talking about this? Hello, class, can you hear me?
Yes, sir.
Yes.
Yes. So Kashish, you were talking about that very point? This one?
Yes, sir.
This point you are talking about,
Yes, sir.
right? Now see,
हाँ जी.
I am saying if f is constant. Now, if you are saying a function is constant, then it means, let's say it can take a non-zero constant value or it can take a zero constant value, right? Because you can have constant to be zero, you can have constant to be non-zero. Is that okay? For
Yes,
example,
sir.
if say I have a constant function in real valued functions, for example, then your function can be fx is equal to 2 for all x. One example is this. Or you can take fx is equal to 0 for all x. Another can be this. So first of all, I have divided the constant functions into two classes. One is if the constant function is of this type, when its values are non-zero. Is this okay? The second is when it is zero. Is
Yes,
this
sir.
clear? Is this clear up to this stage? But if our
Yes,
function
sir.
if our function is of this type, then certainly there will be no z at which the value of function can be zero, because by definition here now, by our choice, because alpha is non-zero, so you can't have any value of z at which function can be zero. Yes or no?
Yes, sir.
Right? And that will not that will be against the given fact that it is given to us that there is one element at which the function is vanishing. It
Yes,
means
sir.
if function is constant, then it can't be a constant function of this type where alpha is non-zero. Certainly it can't be of this type. It has to be of this type, because only then and then you can fit in the condition that the value of at a is given to be zero. That is number one. Is this okay?
Yes, sir.
And now, because our function is given to be non-constant, yes or no?
Yes, sir.
So it can't be zero at all z's, because if it is zero at all z's, then it will be a constant function. That will be a violation to
Yes,
that
sir.
condition. So certainly our function should be of this type, that it should be possible to have its value zero at some point, and while at other points it must be non-zero, because if it becomes zero at all points, then it will become a constant function. That is a violation to this condition. Is this okay? So by this kind of exhaustive argument, exhaustive means that we have eliminated one by one. We have ruled out the possibilities one by one. Is that okay? So that's
Yes,
why
sir. No, it is.
our function can't be identically equal to zero, right? Okay. So let me take your attendance, class.
In this theorem, we can say that gz, which we have created in the previous theorem, can serve the purpose.
Ashish, the ZZ created in the previous means you are talking of ZZ of the type Z minus A to the power M into FZ. You are
Yes, sir.
talking of that ZZ.
Yes, sir. So we have shown that fz is equal to z minus a to the power n into zz.
Yes.
And zz was
Yes, actually, the point is that the my problem is only that Ashish, though I can't say it precisely right now, but the my idea is that if you take gz to be of the type x minus a to the power m into fz, right? Then actually you are specifying the function, and I don't understand, because we are given that the multiplicity of the function f for the root a is 1. We don't know whether it is a multiple root or not. So I don't know whether the question which you are asking is in this context is a well-defined question or not. Uh, I mean, I can't say. I mean, are you getting my point? I mean, I can't say whether your question fits into this frame or not. I don't know. Um,
Okay, sir. Okay.
yeah, I mean, I don't know how to answer this. I don't know. That is a random question. I don't know. Maybe I will give it a thought. Maybe your question has some point, but right now I'm unable to see any point in this question. But maybe I think you are talking of the function gz is equal to x minus a to the power n into fz, na?
So I am just saying that the GZ which we have created in the previous theorem,
Yes.
from that we can use the, from that we can prove that 3.10 corollary or not, because it was
No,
not
I can't say. Ashish, I'm sorry. I have not looked into that aspect. But anyway, if, once you have raised the question, I will give it a thought whether the question makes sense or maybe the question makes sense and I will look into it if it is possible. If the question makes sense, it is meaningful, then maybe that choice of G will work. So I will have to look into it. I'm sorry, I have not I have not looked into it that way because certainly you can understand that whenever we do any concept, there may be several questions that whether we can approach like this or like this, and very often for an individual it is really something very, I must say, that to look into all possible approaches, to look into all possible things, certainly it becomes really difficult, but certainly you have raised a question, so I will look into it whether that question makes sense and whether we can make use of that kind of G. So I will have to look into it.
okay. So I
I
was
mean,
just thinking, so just
no,
I
it's okay, but for me, but for me, each every question of each one of you is important because maybe apparently sometimes it so happens, Ashish, that we don't see a substance in the question asked, but when we look into the question very closely, then I have found that sometimes the question has got a substance. So maybe if I give a close look to your question, maybe in this regard, we don't get anything out of this question, but sometimes uh, one may get something else out of a good question. So right now, because I'm not convinced whether the question is well defined or not, but if I find it is well defined, maybe if it does not fit in this frame, maybe it may give us some other important information if we look into this question closely. So that's why I can't ignore your question. So,
okay, sir.
so that's actually a problem. Whenever any one of you asks me a question, so I will have to take up that seriously because you never know that. So many students are attending my class. I don't know that who one of you is so good at mathematics that may have a different idea about some particular concept, and that will be a learning to me. Actually, that will be an addition to my learning. This is something to which any teacher actually eagerly waits, to some addition of knowledge, to some addition in his or her knowledge. So I will look into this question, Ashish, definitely.
Okay, sir. Thank you.
Okay, so let me take your attendance. Someone has raised hand. Yeah, Amar, you want to say something? Uh, um, Sorry, just a minute, class. Just a minute. Amar, you want to ask something? You raised up your hand. Okay, class. Thank you very much. I have taken your attendance. So on Thursday, we will start with maximum modulus theorem. Thank you, class.
Thank you, sir.
Okay.